Calculus. Many have wondered of its origins. Many have concluded that it began with Sir Isaac Newton, but little did they know, calculus itself was around since the dawn of time.
Yes.
Who's Taylor and what's the series?
What's the Euler's method?
What's the variation of variables? What's the mean value theorem?
How do you find speed?
Where's the Big Mac guy?
Okay, this is basically question number 3 of the AP Calculus BC 2012 exam. Alright, I'm gonna rush through this this presentation real quick because 11 minutes is way too long, so here we go. Let's read the question. Let f of be the continuous function defined on from -4 to 3, whose graph consisting of 3 line segments and a semicircle centered at the origin is given above. Let g be the function given by g of x equals the integration of 1 to x f of t dt. Alright, part A asks us to find the values of g of 2 and g of -2. Okay, since you're given the graph of f already and the equation, you would just use that. You use your equation and then you substitute in 2. So g of 2 equals your equation with 2 substituted into the x. And then basically integration is area, and you're given the graph of f already, so it looks like a triangle from 1 to 2, so area of a triangle is BH over 2, base times height over 2. So it's 1 times 0.5 over 2, what's half of 0.5? It's 0.25. Alright, part B asks us to find the value of the derivative of g at -3 and the second derivative of g at -3. In order to do that, you would have to realize that since g of x equals the integration of f of x, that means the derivative of g of x equals f of x. So, knowing that, you would find g of -3 on the graph of f at -3. So at -3 on the graph of f, the answer would be 2, and that's your answer. And to find this, you would have to find the derivative of f at -3, and which would, oh, here it is. And then how would you find that? You would use the mean value theorem, which is seen here. And then to use the mean value theorem is you just substitute in your numbers. It's 1 minus 3, -4 minus -2, which is -2 over -2, which is 1, and that's your answer. Okay, part C asks us, find the x-coordinate for each of the points at which the graph of g has a horizontal tangent line. So basically you find the maximum or minimum. And to find the maximum and minimum, you would need to find your first derivative at 0. And then since g prime equals f, so you just look on the graph of f to see where it's 0, and you see it is 0 at -1 and 1. And then here's your explanation. You have to look at -1 and see, you can see it's the max because g is increasing from -4 to -1 and decreasing from -1 to 0. Therefore it's a max. And for x equals 1, there is no max or min at x equals 1 because the graph of g is decreasing from 0 to 1 and 1 to 3. You can see that on the graph of x. And for part D, here's part D. It asks for the point of inflection. To find the point of inflection, you have to know that the second derivative of g equals derivative of f. And you see that to find that, you would have to find the zeros of f prime. And you see zeros at -2, 0, and 1. and then you have to state some statement. So there is a change in concavity on the graph of these, on the graph of G at these points here, and that's it.
And that's how it's done.
For t is greater than or equal to 0, a sphere is moving along a curve so that its position at time t is x of t, y of t. At time t equals 2, the sphere is at position 1, 5. It's known that dx over dt equals the square root of t plus 2 over e to the t, and dy over dt equals sine squared t.
Is the horizontal movement of the sphere to the left or the right at times t equals 2? Find the slope at t equals 2. To find the slope, you set the dy equation on top of the dx equation. And since you're finding the slope at t equals 2, you substitute 2 in for t. After plugging it into the calculator, you end up with 3.055.
Part B says find the x-coordinate of the sphere's position at time t equals 4. Okay, so since we're asked for the x-coordinate of the sphere's position, we use the dx over dt equation, and that's in first derivative form. So we have to take integration to get the position. So that would be x of 4 is equal to, and make sure you don't forget the 1 because that would be your plus c. Integration of 2, 1. And then your answer should be 1.253.
C. Find the speed of the sphere at time t equals 4. Find the acceleration vector of the particle at t equals 4. Great. So this is the speed equation. It's the square root of the first derivative of x plus the first derivative of y. And since you're looking for the speed at t equals 4, you're substituting 4 in for t. After plugging this into the calculator, you get 0.575. To find acceleration, you need to find second derivative. The first derivative is given already, so you just find the derivative of that to find the second derivative. You're looking for acceleration when t equals 4, so you substitute 4 in for your t, put it in your calculator, and you get negative 0.041. You do the same thing for the dy. Don't forget your chain rule. You put 4 in for t as well, put it in your calculator, and get 0.989. So this is your x, and this is your y, and you use vectors.
Find the distance traveled by the sphere from time t equals 2 to t equals 4. Okay, so since it's asking us to find the distance traveled from time t equals 2 and time t equals 4, you take the integration of the speed equation. And then, so you would have and make sure you square them. And your final answer would be 0.651 after you substitute it into the calculator.
Well, I don't want my meat raw, honey.
We need to raise the temperature.
How do you reckon you do that?
Calculus, that's how.
So beginning with question 1, we had to use the data in the table to estimate the derivative of W12. And to do this, we must use the mean value theorem. And by using the table given, we are able to figure out that between 9 and 15 minutes, the temperature of the water increases at an average of 61/60 degrees Fahrenheit per minute. And so, the next question, we must use the data to evaluate the integration of derivative Wt from 0 to 20. And using integration, we're able to find that since we begin boiling the water at T equals 0, the temperature has increased 16 degrees Fahrenheit after 20 minutes. So beginning with the next problem, we must use a left-Riemann sum with 4 subintervals indicated by the data in the table to approximate 1/20 of integration Wt from 0 to 20. And we must determine whether this approximation is an overestimate or an underestimate of the average temperature of the water over these 20 minutes. And by using a left-Riemann sum, we're able to find that the average temperature over these 20 minutes was an underestimate because we end with a positive number. And if you were to graph it, the temperature would end up concaving up. And beginning with the next problem, we're given a model. And based on this model, we must find what the temperature of the water at time t equals 25 is. And so by using simple substitution and integration, if we were to continue heating the water, the temperature would decrease to 69 degrees Fahrenheit at time t equals 25 minutes.
That looks just about right.
That's right.
Last race where every car was running at the finish, as we have
It's a damn fast race car. How fast do you think it went? I don't know. How far do you think that is? Can't tell me on damn TV. Obama bring the metric system. My great man. I was supposed to know how far it went. Cool. Like I'm fucking stupid? Just give me the damn numbers Obama making them give.
So for part A, we have to find the tangent equation. We know that f1 is our y number, which is 15, and the first derivative of 1 is 8, which is our slope. So we have to use the tangent line equation. So the equation will be y equals 15 plus 8, parentheses x minus 1. So we will substitute 1.4 into the equation. So we will get 15 plus 8, in parentheses 1.4 minus 1. So then it will become 15 plus 8 times 1.4, which will become 18.2. Yeah. So for part B, we'll have to find the midpoint Riemann sum. We'll be using the midpoint Riemann sum equation to use the numbers 1.2 minus 1, then multiply that by 10, then we'll add 1.4 minus 1.2, then multiply that by 13, which are the middles of those two sections. And the answer will turn out to be 4.6. Yeah. For the second part of the question, we'll have to find the approximation of the integration of 1 to 1.4, the first derivative of f. So we'll have to use f1 plus the integration of 1 to 1.4 f prime. By doing this, we'll be able to find the approximation. So we will be using 15, which is given as f1, and then we'll be using the integration of 1 to 1.4, which is 4.6. So we just add them and it will become 19.6. So for part 2, we will be using Euler's method to find 1.4. 1 and 15 are given. Dy or dx is also given because of the graph. delta x will be our 0.2 step size to get to 1.4. We multiply 8 times 0.2, then we add delta x to 1, then delta y to y, which would give us 1.2 and 16.6. Then we'll just repeat the whole method again, which dy over dx is our second derivative for our first derivative for 1.2, and the answer would be 19. So for part D, we'll be looking for the Taylor series, where we'll be starting at x equals 1. The x equals 1 will be represented as in the parentheses x minus 1. Our first number is 15, then our first derivative is 8, and so on and so on. So at PC we'll be simplifying, so it'll be 15 plus 8 times 1.4 minus 1 parentheses plus 10 because of 20 over 2 factorial, so 20 divided by 2 is 10, and then parentheses 1.4 minus 1 parentheses squared. As we simplify that, it will become 19.8, and that's number 4.
Now just hit that damn Jaguar! Obama killing our planet. Obama carrying my ass.
Dora, there seems to be a problem.
Seems to be a problem.
I think McLaren's approximation about alien life forms was correct.
There's alien life forms out there.
I think so. Oh, where did you hear that?
Yeah.
We're getting closer. We're
We're hitting the atmosphere.
For this problem, they state the function g has derivatives of all orders, which is not really important, and then give you the Maclaurin series for function g shown here. For part A, they asked to use the ratio test to determine the interval convergence for the Maclaurin series of g. So the ratio test looks like this. You substitute in n plus 1 where n's are shown. Looks like this. See here, n plus 1 substituted. Then you simplify by multiplying by the reciprocal of this bottom fraction, and eventually simplify down to this, negative 1 to the n and negative 1 to the n plus 1. So here the n's would cancel each other out. Now you have to find the limit of this function. So the limit as n approaches infinity, and keep in mind this is all an absolute value. As n approaches infinity, you're left with x squared. And this negative 1 disappears because it's an absolute value, so you're left with x squared now. The interval of convergence would then be 1 is less than 1 and greater than negative 1. But you have to test both endpoints to find if they converge there. So in order to do that, we go back to the series. And test those endpoints using the alternating series test. Basically use negative 1, so where x equals negative 1 in this equation, you would have something like this. So now the final step to find the interval of convergence is to test both endpoints. So at x equals negative 1, you would substitute in that into each term, and your series would look something like this. Now the definition to find if it was converging is the absolute value of each term as the series goes on should be approaching 0. So So the series should be getting closer to 0. As you can tell, the denominators are getting bigger, therefore be approaching 0. And then you test the next endpoint, which is at x equals 1. And same thing, you get 1/3 minus 1/5 plus 1/7. Take the absolute value of each term, and they would be approaching 0. Therefore, the interval of convergence for this series is x is greater than or equal to, greater than or equal to -1 and less than or equal to 1. And there's your interval of convergence. So for part B, states the Maclaurin series for G evaluated at x equals 1/2 is an alternating series decreasing to 0. And the approximation for G at x equals 1/2 using the first two non-zero terms, this first term and the second term, of this series is 17/120. You have to show that this approximation differs from G at x equals 1/2 by less than 1/20. So basically you would take the next term and compare those. See if it's less than 120. So it would look something like take this next term, right? Substitute in 1/2 x where x is, and you solve this out. So you would get, I'm just going to speed through this, 1/224. 2 to the 5th is 32. 1/32 divided by 7 is 1/24. Now that is less than 1/200. Oopsie. Okay, yeah. That's worth 2 points. For this next part, C, really simple. That asks you to find the first 3 non-zero terms, for example 1, 2, 3, and the general term. Don't forget the general term of the Maclaurin series for G prime of x. So you would take the derivative of each term and the derivative of the general term of G of x. That would look something like 1/3, taking the derivative of this first term, then the second term. X to the 3rd over 5, so 3/5 x squared, 5/7 x to the 4th. Then the general term, taking the derivative of the general term, this is G of x and this is G prime of x. Since this -1 to the n and this bottom denominator 2n plus 3 are constants, you don't take the derivative of those, you just rewrite them. This is your coefficient, so you would take the derivative of this, bring down the power and subtract 1. Here I brought it down, and then subtract 1. 2n plus 1 minus 1 is just 2n, so this is your general term for G prime of x. Let me just put that in. Well, you get the idea.
Day 1. This is what the egg looks like. We will check back in 1 week to see how much it has grown. Day 7, it has grown very, very large in just 1 week. We will check back in another week. It is week 3 and the egg has gotten very big and it's just about ready to hatch, so 1 more week and there should be a baby bird. It's now week 4 and the egg has just hatched. The baby bird weighs about 20 pounds and we will continue to see how fast it grows.
To find the second derivative, you implicitly derive the first derivative given above. Then you resubstitute your dB dt and simplify. Since b is concave down from 20 to 100, the given graph cannot resemble b. To find the weight at which the bird is gaining weight faster, you substitute in 70 and 40 into the differential equation given above. And since dB dt of 40 equals 12 and dB dt of 70 equals 6, the bird is therefore gaining weight faster at 40 grams. To do separation of variables, you split up 100 minus b and 1/5. You then integrate both sides and get negative ln of 100 minus b equals t over 5 plus c. To find c, you substitute in your initial condition 0, 20 and find that c equals negative ln of 80. You then solve for b and find that b equals 100 minus 80 e to the negative t over 5.